So we're really just delighted and honored to have Professor Guido Imbens of Stanford here to present. I know Guido well, as we were colleagues here at Berkeley for 5 or 6 years. And in addition to all the honors I'm going to talk about, I'll just say he was a great colleague, good friend, and it's just wonderful to welcome him back to Berkeley. Guido graduated from Brown with his PhD. He's taught at Harvard, UCLA, and here at Berkeley. He was awarded the 2021 Nobel Prize in Economics together with Dave Card and Josh Angrist for pioneering work on causal inference and really bringing a new clarity and credibility to economics research. And he's also a fellow of the Econometric Society, the American Academy of Arts and Sciences, and many other honors. Today, Guido will be speaking about In Search of the Third Number. We're very excited to learn what this third number is, Guido. So thanks for sharing it. And really, I just want to give him a very warm welcome and thank him for joining us.
Thanks very much, Ted. Thanks for a very kind introduction. It's always very nice to be back here in Berkeley. I had a very enjoyable time here, and there's many days where I wish I was still here. I can't really say that too often at Stanford, but I did have a very nice time. It was a great, incredibly collegial department. And so I have great memories from here. First, I should also apologize that I misspelled the acronym for BITS, the Berkeley Initiative on Transparency in the Social Sciences. So the second T should be an S. So actually, the second thing I should mention, this is joint work with Susan Athey, also from Stanford, who's actually also here at Berkeley today, giving a different talk in the computer science department, so she couldn't be here at this talk. Next thing, Ted mentioned the title, In Search of the Third Number. I really like the title. We don't actually have a paper yet. We just have a set of transparencies and a set of ideas that we talk about regularly, and hopefully we'll get to a paper. But before talking about what we're in search of and what we're trying to look for, I just do want to make a couple of general comments on transparency and replication and things BITS has been involved in. It's sort of clear there's been a huge, so partly I want to do this from the perspective of one of my other roles. I'm the main editor of Econometrica, one of the main journals in economics. And although we have not really been a leader here, I think the fact that a lot of the journals now have much better replication policies in place, and their kind of leading role was really played by the American Economic Association. I think that's been incredibly important, setting up a data editor, and now we have appointed one as well, who's starting in July. But I think that's really been incredibly important, and I think that's making the research in economics better. And there's still kind of a long way to go. In some sense, I was actually very pleased to see the Review of Economic Studies recently retracting a paper. It's quite amazing in some sense that there have been so few papers in the main economics journals that have been retracted over the years. If you compare that to the other sciences, you could interpret that as evidence that we are just very good at research and nothing needs to be retracted. But I think that is clearly not right, and it's just we haven't done a very good job in figuring out when to retract papers, and the fact that that's happening more now is very important. And I think we're going to see a lot more of that now that people have to make data available, and so there's actually the possibility for seeing that something went wrong in a paper, and that that shouldn't be the end of things. That shouldn't be the end of the world when that happens. We should recognize that published papers are not necessarily the final word on a particular issue, and that it's always going to be an ongoing thing. And so again, I think we'll see more of that, and it'll become a less big issue. And I think the quality of the research will get better. I think we need to do a better job still training the students so that they write code and they do empirical work in a way that's directly replicable. When I see what happens at the final stage in the journal process, when we say, well, now we actually need the files to get everything replicated, it's very disappointing to see that in many cases that then still takes 4 to 6 months. And it's clear that all along the way, people should have kept records so that at that point they could send the stuff the next day and it's all ready to go. And I think that's partly a reflection on our failures in the graduate programs to teach the students how to program in a way that's replicable. You know, if I look back at the time when I did more of my own coding, I might write comments in the code in Dutch, and I would have conventions that were special to me. And clearly that was very bad in terms of how to code. And when I see now at some of the organizations I'm involved in, through consulting relationships, how they code there, where the template is, if I code something, I need to pass it on to a second person who needs to be able to make changes and pass it on to the third person. And by the time it gets to the sixth person, it still actually needs to work, and people still need to be able to change things in the code and make it work. Those are really the important things, and we don't at the moment systematically train the students to do that. And so I think we need to do a better job there, kind of in the first year programs. And again, this is partly on us, and we're trying to kind of now tell people when they submit papers, be aware that if this ever goes further, you need to have the files ready. And if things get delayed at that point, we may end up rejecting the paper just because you didn't keep good records. If the results change at that point, then all bets are off. But we need to train the students better in the econometrics course, and I think traditionally we've done a very poor job, and that includes myself. We've done a very poor job in many of the programs. So then on to the topic of this paper. And so at some level, this actually also came out of some of the involvement I had with other organizations, where often there were sort of stylized version of what was happening was someone had to make a decision to implement something or not. And the decision maker was uncertain about that. There was some data that reflected on the effects of that. They wanted to know what would happen if they made that decision versus if they didn't make that decision. There was some data available that could shed light on that. They tasked a data scientist with analyzing those data and reporting back to the decision maker. And then there was going to be a meeting where they would talk about the results, and then the decision maker would make that decision either on their own, or there would be some process for making a decision. And so what I want to think about it here is sort of what the data scientists should report to support the decision making, or in other words, how the evidence from the data should be summarized. And in particular, kind of what information the data scientists could supply to support the credibility of the basic estimates. And so, and this is sort of where the title comes from. In a lot of these meetings that I've been where I was present, the first thing people would report is sort of a best estimate as to what the effect of that intervention would be. And so kind of in a simple case, and I'm mainly going to look at a case where there's just some intervention you apply to a number of clients or customers or units, and you want to know what, and the main quantity really is the average effect of that intervention, if we apply it to everybody, to the whole country, or not at all. The second number is some measure the precision of that first estimate. Are we really very sure about that? And in particular, kind of the statistical precision of that estimate. And so that can be in the form of just a standard error or a confidence interval. And I'm going to use this pretty much interchangeably. Kind of often it's based on a normal distribution. So the confidence interval is just the point estimate plus or minus 2 times the standard error. But then after that, things kind of would diverge a lot. What would be reported after that kind of would vary a lot from context to context, from analyst to analyst. And it's sort of, it seems at some level surprising that we would have a lot of agreement on what you should report, what the first 2 things would be that you should report. But if the decision maker was actually sophisticated enough to take in more than just those 2 numbers, it wasn't really clear what else we should report to them. And so what we're thinking about here is what else, how much structure can be put on what else people should actually report, so that it wouldn't depend as much on the individual data analyst, what their favorite statistical method was for supporting that evidence or what they would do, or kind of another, sort of more, in a more nefarious interpretation. We don't want to give too much freedom to the data analyst to then supply things that agree with what they think should be done, but put some discipline on that to make sure that we're making these decisions over time for a number of different decisions, making them in a systematic way, rather than one time focusing on one particular problem and the next time focusing on a completely different problem. And so kind of part of the parameters of that discussion is that these first 2 numbers are actually very useful. And there's a nice paper by Isaiah Andrews and Jesse Shapiro, kind of where they say that even if people have prior distributions, reporting the point estimates and the standard errors is very helpful, because then the decision maker can combine that with their own priors, and so you don't actually need to know the priors beforehand to still make sense of those numbers. But the question is what to report beyond that. Of course, at some level, if the decision maker is very sophisticated, we can just give them all the data and they can do anything they want. But the task here of the data scientist is really to summarize that and break that down to kind of just a small number of things that are the most relevant. And so I'm going to look at a very specific setting here. I want to think about a decision where we have a large population of units, and the decision is going to be either expose everybody to this new intervention or nobody. And the decision maker cares about a particular scalar outcome. And so at some level, you can argue that all they care about is the 2 distributions, the 2 marginal distributions of these outcomes. And the scientist gets information on a number of for a number of units on the outcome, the indicator whether these units were actually exposed to the new treatment or not, and possibly some other covariates. There could be more complicated decisions where some units are assigned to the treatment and others not, based on information. I'm going to stay away from that for the moment. I'm also going to assume that the data scientist doesn't actually know the prior distribution of the decision maker, so we can't directly combine that. And so I want to again start with the first 2 things that the researcher is going to report, namely the point estimate and the standard error. But then I want to divide, sort of organize the other things that the data scientist might want to report into a couple of different categories. So the first pair of statistics are sort of relatively objective. They're properties of the data set. Well, and I'm not quite sure exactly how to label this, but these are things that you can directly calculate. So one question is whether the point estimate is actually the distribution of the estimator is actually approximately normal around some limiting value with some variance, where that variance is the square of the standard error you reported. Is that estimation strategy credible for that particular statistical object? I want to keep that a little bit separate from whether you're actually estimating the right thing, but just whether the methods are actually delivering from a statistical perspective what you're telling the decision maker they're reporting, whether the statistical methods themselves are credible. And I'll come back to that, kind of what particular things are helpful there to look at that. Second thing is in this context, it may be important to know for the decision maker whether the average effect is actually representative for the population. And there's sort of two parts of that. One is the decision itself may be quite different, even if the average effect is 10, if the individual effect is 100 for 10% of the population and 0 for everybody else versus 10 for everybody. That may depend on the preferences of the decision maker. They may care about the inequality in the population, and so just the average effect itself, even if you estimated that well and precisely, may not be the only thing the researcher, the decision maker cares about. That's all. The heterogeneity is also going to be important for one of the second things about the external validity, because whenever we do one of these analyses, we can never be sure that the results have external validity. We do an analysis now and we're trying to influence policy or help decision makers make decisions that are going to be implemented in the future. And so the future population may be different. The world is going to be different. And so there's no guarantee that the results that we obtain from the past are going to be valid for the future. But it's more likely that they're going to be valid if we find that the effects are the same for lots of different groups. If we find that there's very little heterogeneity in these effects, then it's much more plausible, even if we still can't guarantee that these effects are going to be helpful in predicting what's going to happen for other populations. If, on the other hand, we find that for some particular populations, the effect is really big, and for others, it's negative, and for others, for the third group, it's 0, then we know for sure that it's going to depend on what the composition of these future populations is. And if the composition itself may change, you're going to be much more uncertain about what the effect is going to be in the future. So thinking about the heterogeneity is going to be important, even in the absence of decisions that directly depend on the heterogeneity, even if we're not going to assign some people to this intervention and others not. And the third thing, so this part of this more subjective set of statistics is about the internal validity. Do we actually think what we are estimating in this data with some precision, but sort of if we had a big enough data set, well, the limit of what we're estimating, is that actually telling us, are we convinced that that's giving us the right answer about what the average effect is of the treatment? And so that is, in a sense, reflecting on the identification strategy that is being used, the credibility of the variation that is being used to estimate these things. And we can, again, I'm going to look at a couple of different ways we can look at it, but essentially it's going to be sometimes there's direct analysis we can do that tell us, no, here, these results really are not credible. And or in other cases may tell us, yes, these at least seem to have some plausibility. Other cases, we can do sensitivity analysis, but we say, well, in this case, things are not too sensitive to minor deviations from the critical assumptions. And in other cases, they are in fact very sensitive to these to deviations from the critical assumptions. And then the last category, and there I'm not going to say an awful lot about it, but when I was talking about this work in early January, I found myself on the plane from San Francisco to New Orleans for the AEA meetings, and I was sitting next to David Card for 6 hours. So I got to benefit from his thoughts on this. And he thought that context was very important here. And so what he meant by that, and sort of how I'm going to interpret is that in many cases, we're reporting numbers where we actually do have some prior information from other studies, maybe not quite studying the same question, maybe looking at related things, and it's going to be very different if we have a result. Suppose I'm estimating the returns to education, and I have a particularly clever data set and a clever strategy for estimating it, and I end up with estimates for the return to education of per year of 20%. That would be very different from finding 6 or 7%, given that much of the literature says, well, it's somewhere between 5 and 10%. If you find a very different number, you clearly want to flag that as this is something unusual. Maybe we should be more worried here about what's going on versus this is in line with what we've seen before. So, so let me kind of now start kind of with a very simple example, and I'm not going to get much further than that simple example. But so suppose we actually have a completely randomized experiment. We estimate the average effect. We report the standard error calculated in this way. So first question is kind of, are there any cases where that's all we need to know? Is there any case where we say, well, that's done. The rest of the data you can just throw away and there's nothing more you need? Well, suppose that we're actually really sure that the outcomes are all normally distributed, and we're really sure we had a randomized experiment, and we're really sure that the variances in the two groups are the same, and we have a large enough sample that we estimate these variances, and then you could argue that there isn't really much else we would need to know. There isn't really that much else that would be important. But sort of clear that it's clear that that's very unlikely to hold in practice. Even if we have a randomized experiment, the distributions could be very non-normal. They could be outliers. The effects could be very different for different parts of the population. So almost in all cases, it's going to be very helpful to think about other things to report. And so I'm going to run out of time soon, but so I want to bring up kind of some of the specific things here. One is that if we worry, even if we have a randomized experiment, it's unlikely we have homoscedasticity, it's unlikely we have normality. So it'd be very useful to also explore the differences between the two distributions beyond the differences in the center of the distribution. And so one thing you could do is look at the differences in quantiles of the two distributions. You could look at more robust estimators for the center of the distribution. And some of the applications have been involved in some of the tech companies. You get these distributions that are vastly more thick-tailed than what you see in economics, and being very careful about looking at differences in quantiles is going to be very, very helpful. Now, let me then kind of go on to mention the sensitivity analysis, and then we're going to make one comment on when we actually have covariates. But if we're worried, then in fact the assignment was not random, and possibly even in the presence of covariates, if we think that the assignment is not random conditional on covariates, we may want to do some type of sensitivity analysis where we explore how sensitive the results of basically comparing differences in means in homogeneous subpopulations, how sensitive those results are to the presence of unobserved confounders. And at some level, this goes back to two strands of the literature, the Rosenbaum-Rubin literature on sensitivity analysis and omitted variable bias, the formula from the traditional econometrics literature. The bias comes from the fact that unobserved confounders affect both the outcome and and are correlated with the treatment. And so there've been a whole bunch of proposals in the literature now for exploring how sensitive the results are to the presence of unobserved confounders and how you can link that to correlations with observed confounders to get systematic ways of exploring the sensitivity. Then if we actually have the covariates, what is very helpful to do is to explore the variation in the average effects as a function of the covariates. Especially, there's been a lot of work on doing that in high dimensional settings where there may be a large number of covariates and standard methods don't work particularly well. But we can both test whether there's evidence of that variation, and we can try to directly estimate the average effects in various ways, and use that to report some of the evidence on that is important beyond simply reporting the average effects. So let me now go to the last slide. It is where we started was the fact that we were kind of confused by the widespread agreement that starting an analysis, starting a report, always focuses on essentially the same two numbers in a wide range of settings, but that there is much less agreement on what we need to do after that. And so what we think would be helpful, partly in regard to the transparency of the analysis and to make it easier to communicate the results of different analysis, to have more of a template of what other information is helpful to communicate to decision makers. And we think of them as sort of fitting into three sets of categories. Do the statistical methods actually work? Kind of, are they reliable? Do they give us confidence intervals that tell us where in a large sample the parameters would actually be? Is there heterogeneity in the effects we're looking at, or are these relatively homogeneous? And then the more subjective analysis about whether the things we're trying, the things these analyses are estimating are actually giving us the things that matter for the decisions we want, or whether there's the concern about that, and whether they would extend to other populations than the ones we've been looking at. So let me stop here and open up for any questions.
Hey, so if the motivating question is what should drive a policymaker's decision, like, shouldn't we want to know something about the cost of implementing the program? So wouldn't we want to know, like, what's the probability that the treatment effect that you're going to get in whatever population you care about exceeds the cost of implementing the program?
Yes, clearly that should be part of the decision. And so in many of the cases, sort of where I drew my inspiration from, sort of the cost was relatively clear. So the decision maker would actually know that part, but the decision maker was not clear about what the consequences would be of the program, and sort of how robust the results would be. But in case there's other cases, obviously, where the cost is also uncertain, and then in some sense the outcome should be transformed to the net outcome, net of costs.
Hi, Eric Van Duzen, UC Berkeley. I thought it was interesting to think about where we teach people. Maybe we teach people 1A and a little bit of 1B, and we don't really teach students like 2A or 2B. And I just had a question to you of like, where would we be like introducing that into the curriculum to teach the students the second half?
Well, I mean, I think no, I think the heterogeneity in the end is very important, and we need, you know, exactly how well, at what level of sophistication we would teach that early on is sort of debatable. But you can teach it kind of very simply by just breaking the data set up in different ways and looking at the implications, the estimates of the effects for these different subpopulations. And you can do that systematically, kind of doing one covariate at a time, splitting it at the median. There's a papers and proceedings paper where Susan and I kind of looked at that way of analyzing robustness, but I would give you a quick handle on most of the major components of the heterogeneity. But I think it's something that, again, in many of the places where experimentation is being done at the moment, where that's very important, where there's just huge amounts of heterogeneity, where vast subpopulations are not affected at all, but some are affected in major ways, and that clearly leads to very different implications for the decision makers.
No, I don't know if this should be the last question. Yeah, so I just have a practical question on your observation at the start of your talk about the importance of documenting code so that others can use it. And I'm wondering, do you have a view on the value of the AI-powered tools like ChatGPT to do that work, not only for the code that it generates, but for code that others generate?
Yeah, I mean, I think for coding, clearly ChatGPT is just incredibly useful. I mean, I'm not speaking from practical experience here, but sort of what I've seen other people seeing other people use it for coding, it's clearly incredibly helpful for increasing the productivity of anyone coding, but because you need to build in checks the same way we always do. But it can certainly help improving the hygiene of the coding, kind of by using more conventions and making sure they become more widely used. So I think it's going to be, I mean, I think it already is an incredible tool there, kind of not just ChatGPT, but Copilot, kind of in some of the GitHub environments. So I think that's good to help. But I think partly sort of traditionally in the econometrics courses, we didn't really spend much time on teaching the students to code well and to do it in a way that was replicable. We were teaching them to kind of get the answers rather than having documentable answers. And I think we need to change the focus there. And so from that perspective, I think at the moment, replicating papers takes a long time. But once, in 5-10 years, once the people were trained now to code in a better way, writing the code for the papers, it's going to be much easier, and the practice will be much better.
Thanks. Seth Gars from the Gates Foundation. It strikes me that you said something that could potentially have really deep ontological implications for what we think of as research. And let me explain. So in your thought experiment, you limited us to a data set, and we don't know anything about priors or need to know anything about other people's priors. But one of the motivations for this third parameter is potentially knowing something about external validity. And so the constraint of the thought experiment biases, I think, us towards looking at the internal heterogeneity using something about, because we can't know anything about the external world, right? but that's really what we want to get at. And if we had like a very selected sample, which we often do in development economics, we struggle to say, you know, how relevant this is for the broader population. We might have no heterogeneity in our sample because it's a population of rural micro entrepreneurs in rural Tanzania. That doesn't mean that the lack of variation there suggests that there should be homogeneous treatment effects if we were to think in terms of external validity. So the existential, ontologically fascinating point here is potentially that we can't say anything meaningful from a research perspective unless we say something about how that sample fits in the broader world. So, yeah. And the final point is this really relates to something Ruth said earlier, which is the value of descriptive research. On one hand, we do this in all economics papers. The first table is always just a descriptive table, but we rarely go beyond that to say, okay, the fact these are just pure descriptive parameters suggest this is totally selected population where we can't say much externally or vice versa.
Yes. So in some sense, what I have had in mind for saying that data set gets, the data scientist gets handed a data set that has outcomes and these other things, that could actually be a much bigger thing. There could be multiple data sets that are combined and data sets that have different configurations of data. But I wanted to start kind of by saying, okay, even in this well-defined context, it's not clear exactly what we should be looking at, but you could make part of that what the data scientist is doing also is looking for data sets that could actually be helpful for making these decisions. Now, starting at the other side, so partly what I'm arguing against is that the focus, what I've seen in a lot of the decision making on just the point estimates and the standard errors, in particular the statistical significance, that is just very misleading, and that's very bad practice. And we need to do much more in tying the data analytics and the data science to the decision making and thinking about making good decisions rather than looking for statistical significance. And because there's been a lot of work arguing that the focus on statistical significance is misleading, but we still see a huge amount of that, and it's bad practice. It's not useful. We need to get away from that, and part of that it may happen through focusing more directly on how we're going to be using the results for making decisions.
Everybody, a round of applause. We're going to break now, and we'll be back at 1:15. There is lunch, I think, outside, just through the doors here. So we'll reconvene in a little less than an hour.